Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 29 in the course Advanced Robotics. In the last class we talked about quadruped gait and we explained that gait is the pattern of foot placement. That is how the quadruped or biped or hexaped is placing its foot on the ground, which foot is on the ground and which foot is in air. That is what the gait diagram shows us. We then started the discussion on biped and we talked about passive bipeds and active bipeds. Today we'll continue our discussion from there and talk about optimization in biped gait. That is, when a biped moves forward or walks forward, then there are infinite trajectories which are possible. How would you choose a particular trajectory in terms of energy optimality? That is what we'll be seeing today. Okay, so today we talk about optimal biped locomotion, that is how to find the optimal biped gait. Now, very quickly revising what we were discussing in the last class is that if you have a quadruped robot like this, then we have to, the first thing that we do is to assign axis. Okay, assign frames or axis, and then find the relation between the local frame. So if there's a global frame here, this is my global frame, and this is my local frame here, then we find the relation between the global and the local, because this is a moving robot. And then in the case of the local, we find the relationship between the foot contact point to the knee joint, to the hip joint, and then to the local coordinate frame. And when it is moving forward, we see that in this particular case, there would be some leg which will be in air and some legs which are going to be in ground. So the way the gait operates is that there are legs in air and there are legs in ground. So in this particular case, we can see that there are 3 legs on the ground and 1 leg is in air. Now the leg is taking a trajectory like this and the body is moving forward by some distance. Okay, and so it becomes 1 leg in air, then all the 4 legs on the ground, and then again 1 leg will be in air. So that is basically what we mean by a gait. We looked at different kinds of gait, for example, creep gait, then we talked about wave gait, etc. Okay. Now from quadruped, this was also an example that we looked at where we have a quadruped robot which is having a creep gait, in which case, in this particular case, only 1 leg in air at any particular instant. Okay, so it is 4 legs on ground, 4 legs on ground, then 1 leg in air, then again 4 legs on ground, then 1 leg in air. That is the gait that it is following. And when the leg is in air, the body also moves forward. Okay, and we also talked about how balance is maintained in such cases. Now let us see further. We talked about biped, then from quadrupeds we moved on to biped robots, which are having 2 legs as the name suggests, and we said that there are active bipeds in which the joints are actuated by motors, which means that the energy for moving the robot forward comes from the motors. But there are also passive bipeds in which there are no motors. And how do the biped walk forward, or where is it getting its energy from? So passive bipeds gets its energy from gravity. That means they cannot walk on plane surfaces, but they can walk on inclined surfaces where gravity is pulling it down and it behaves like a wheel. And this is the very basic concept of what we call a passive biped robot, sometimes also called self-propelling systems, in which like a wheel which is on an inclined surface. So suppose this is my surface and there's an angle alpha there. Then what is going to happen is, because of the contact point here, this mg into that distance will generate a torque about this point, because of which the wheel is going to roll down. So the structure of the robot is also very similar to the spokes of a wheel. So if you look, you must have seen your bicycle wheels. So these are spokes on the bicycle wheel rim, right? So this is your bicycle wheel. So if you just consider 2 of them, if I consider this one and this one, then this is behaving like a section of a wheel. And this one is 1 leg and this is another leg. And based on which this is behaving like a wheel, and it can roll down surfaces. Okay. Now this is a very simple example we had seen in the last class. I'll play it very quickly again. So this is a case of a biped robot, passive biped, which is walking down an incline simply by using gravitational energy. Now this is also a toy, very famous toy, because we can understand the dynamics of biped robots, of passive bipeds, from this very simple example. This walking toy is called tuk tuk, and it walks forward simply by making use of gravitational energy and by moving from side to side. Okay. Today we'll be talking about balance. We'll be talking about active bipeds. Now, before we talk about active bipeds, we have to talk about this concept, what is called balance. Okay, so you understand that if a system is balanced, means it is basically not going to fall down. Okay, so if, for example, if I have a pencil and I try to balance, so this is my pencil, and I try to balance the pencil on the tip, then it's extremely difficult. Okay, it will fall that side or it will fall this side. Okay, so this is what we mean by balance. So very crudely speaking, it should not fall down. Okay, now how can it maintain its balance? We are taught that, for example, if you have an object like this and the projection of the center of gravity is inside the base perimeter, then the system, then it will not fall down. Okay, now this is for a static case where we talk about the CG of the system. But in a dynamic case, there are other forces. So static case basically means it is taking care of the gravity force. Okay, it is balancing or is not getting disbalanced because of the gravity pulling it down, which is basically a static case. In the case of dynamics, there will be other forces which are acting. For example, inertia. If a body is already moving, it is subjected to some acceleration, so there is going to be some inertia forces. There can be other forces like Coriolis force, centripetal force. Okay, then the gravity force we have already seen. Okay, so in the dynamic case, other forces are also acting, and we have to talk in terms of balance of a dynamic system now. And for that, we basically make use of the D'Alembert principle. That is, we convert a dynamic system into a static system at that instant and look for static stability. Okay, so in terms of balance, this is a very simple example of balance which considers only gravity forces, but in dynamic case we have to also consider the other forces. Now, if you are looking at this very simple spring mass damper system, so there is a spring here which you can see, there is a spring there, and this is the top part of it which can rotate at a particular angle about this. So if you consider this to be 2D, and if I say that's my angle alpha and this is the spring deflection which is d, then there are two variables here. One is alpha, the other is d. Now this is a very simple hopping mechanism which works on the principle of, let's see how it works. So you can see that if you leave it from a height, simply by controlling that angle alpha, it can go forward in a particular direction, it can hop in the same position, or it can go backwards. What is it controlling? It is controlling the alpha angle. Okay, so this is a balancing mechanism, very simple balancing mechanism. Let's look at it again. So we are basically controlling that alpha and you're controlling this d. Okay, and how is d controlled? By the height of the jump, and alpha is the angle of this the top body which is pivoted at that point. So simply by controlling these two, what we can do is we can move this forward. It can jump in one place, it can go forward, it can go backward. But something you will notice here is that it cannot stand still in one point. If it tries to stand still in one point, what will happen? It will immediately fall. Okay, why? Because it is unbalanced. Okay, so this is something very interesting to note, that this is something like your pencil here now. If I want the pencil to stand, if I want this to make a point contact there and stand here, okay, it will immediately fall this side or this side. Why? Because it is an unbalanced system. Okay, so similarly, most of these dynamic walkers, when they are on 1 foot stance, they are unbalanced system. This is an unbalanced system, which means that unless you balance the system, it is going to fall. Okay, it is like standing, if you are thinking about yourself and you're standing on 1 foot, and if you're not properly balanced, what will happen is you will fall. That you know. So that means this balancing is something which is very, very important, and it is dynamic balancing, not static balancing. In static balancing, we only talk about CG. In dynamic balancing, it is not only CG, but we will use the term of zero moment point. Okay, so this is one of the earliest robots which are made, and this is basically called the this is also called the hopping robot, one of the earliest robots, which is called the hopping robot. Now, how are we controlling it? There are two variables we are seeing. One is the desired angle, the hip torque, and the gains. So in one case, basically I want to control the hip torque that is going to move the body this way or this way, because we have to control that hip torque tau, and that is basically using a PD controller with two gains. So this is my KP and that's my KD. So this is my position gain and that's my damping or the velocity gain. Okay, so there are two gains which are being used here to control the torque which is acting at this joint here. That is basically going to control the alpha of the body. Okay, so if you want to move it in the clockwise or anti-clockwise direction, we are going to simply change that tau. The other is the force with which it is landing, that FL, which is basically the height that we are controlling. So this height is again controlled by a PD controller. This is my position gain and this is my derivative gain or damping. So this is my Kp and that's my Kd. And by changing both of this, we can, with an adjustable rest length, which is LD. So I'm controlling my rest length, which is LD. Okay, so one, I was controlling the angle here, and next I'm controlling the active length LD here now. So by both of them are being controlled by using the PD controllers. Now, if you look at such a system, this, unlike most other robotic systems we have been studying, they don't move around, right? A robotic arm, when we are saying the robot arm is here, okay, this robot arm is fixed, or at most it can be mounted on a wheeled base, and this moves around. Okay, but in this particular case, it is the robot which is in air is jumping, it's falling on the ground again. So there are different states, and these are covered in what we call by a finite state machine. For example, it has a flight state, it has a loading state. Okay, heel touches the ground and the spring gets compressed. Then there is heel contact being made. Okay, then heel and toe contact has been made, and toe contact unloading, and then goes into flight phase. So first it is here, okay, then it comes down and hits the ground. There is a loading phase which goes on, the spring is getting compressed. Then there is an expansion phase where the spring is coming off, and then this is in flight phase again. So in flight phase, basically leg is in air. In the other phases, the leg is on the ground. Okay, so it's called a finite state machine. So it's like it is moving from one state to another state. What are the states? These are the various states. So flight state is one, loading, heel contact and toe contact. Then there is toe contact, unloading, and flight state again. Essentially, it is in air, which is flight. Then it makes contact. Then there is a loading, which means it is getting compressed. The spring is getting compressed. Then there is a toe off, in which the spring is getting extended. Okay, so this is extended, and then it's in air again. These are the various states in which this machine moves. So what we see is that in the case of a biped robot, the leg can be in air or it can be in ground, and we have to talk about dynamic balance. These are some of the very famous biped robots which are made. One is the Asimo, which was made by Honda Motor Company in the year 2000. It can walk, it can run, it can climb stairs. Okay. Then we have the most advanced robot which is there now is this Atlas. We had looked at Atlas by Boston Dynamics. It can walk outside, it can balance itself in uneven terrain, and it can build a map of itself by using a LiDAR. Okay, for example, we can see that it can walk in different kinds of terrain, and there's another example where it can actually, we can look in terms of dynamic stability. So this gives us an example of so this is what is talking about dynamic stability. So if you push it, okay, it falls down. If it falls down, it has to get up again. Okay, this would mean that there are infinite ways by which you can fall, and there are infinite ways by which you can get up. Which way are you going to get up? Okay, before we come to that, we at least have to talk about which way are you going to walk. Okay, so there is a lot of optimization involved here, because there are very large number of degrees of freedom in the system. Okay, so for any biped robot, let us look at the basic gait pattern, and then we'll talk about optimization. Okay, now when we talk about bipedal walk, the bipedal walk is divided into 3 planes. What are the 3 planes? So if you can imagine a human body here, if you can imagine yourself, you can look from the front side, and if you see from the front side, what would you see? You'll see your head, you'll see your hands. Okay, in this particular case, the hands are stretched out like this. Okay, this is my body, and you'll see the legs which are here. Okay, so this is basically called the frontal plane. So what is called the frontal plane? What you see when you're looking from the front. Okay, now when you're looking for the side, this is my sagittal plane. So when you're looking from the side, what would you see? You'll see your hands which are here. This is the body, and your leg is here. Okay, this is my side view now. Okay, so your hand is stretched out, so you'll see the hand somewhere here. So this is my side view, this is my front view. The side view is called the sagittal plane, the front view is called the frontal plane, and this is also sometimes called the lateral plane. Okay, the lateral plane, sagittal plane are both the same, and in the front you see in the frontal plane. Now if you're seeing from the top, what you'll see is you'll see your head, you'll see your shoulders like that, and you'll see your hands stretched out. Okay, you won't see your feet. Now this is the top view, basically what we call the transverse plane. So this is called the transverse plane, and it's sometimes called the top view. So we have front view, side view, and top view. So this is this is the transverse view, which is my top view. So basically when we're analyzing bipedal gait, we talk about the front plane, the side plane, and the top plane. Why? Because we have to ensure balance. And whenever we talk about balance, we analyze the balance in these three planes and try to understand the kinematics of the system. Okay? So the first question that comes up is how many degrees of freedom is required? How many DOF for walk? Okay, so we are trying to think about how many degrees of freedom only for walking by a biped, for a biped. Okay, so let's talk about for a biped. So I'm not considering the body here, I'm only considering the legs. So in the case of the legs, in the frontal plane, this is my frontal plane, this is my hip joint, this is the knee joint, and then there's an ankle joint which is there. So this is the front view, which I'm writing as F. So these are all the ankle, this is my ankle, this is knee, this is hip. I'm ignoring the top, there is a torso, so I'm ignoring the torso here now. Okay, the left leg and the right leg, they are symmetric and they're equal. So in the front view, this is what I see. Now when I look at it from the side view, what I'll see is like this. It is standing sideways. So this is my hip joint, knee joint, and this is my ankle joint again. If both the legs are together, then they're like this. If one leg is a little bit forward and the other leg is behind, then it is going to be like this. Okay, I hope you can imagine this. So this is two legs in same position, and in this particular case, that is left leg is behind, the rear leg is back, leg is in back, and the rear leg is in front. Okay, so this is how it looks like the side plane. So this is side plane, and this is also the side plane, which we call the sagittal plane. Okay. So when the robot walks forward, basically the robot has to balance. Now what does that mean? We can understand very clearly from here that if the robot tries to lift one foot, now both the legs are on the ground, and if you say the CG is here. Okay, that means both legs are on the ground and the CG is in between the two legs, so it is balanced. If I draw the top view, this will be my one foot, this is my other foot. Okay, and this is the hip joint. So this is what is called the foot perimeter. Okay, so in the foot perimeter, which is made up of the extreme edges of the foot, like this. So this is my rectangle, which is the foot perimeter, and the CG or the center of pressure is inside there and it is balanced. The moment I try to take up one foot, what is going to happen? This perimeter, the foot support polygon or the foot support perimeter, is going to be reduced. So if this one goes in air, what will happen is this will immediately shrink and the foot support polygon will become, so we call this the foot support polygon, will immediately become small now. Okay, so now if it becomes small, what is going to happen? You can imagine the CG is here. So what will happen? There will be a moment about this, and the robot will immediately fall in that direction. Okay, because it's an unbalanced system. So as long as the center of pressure is inside here, the system is balanced. The moment I take up one foot, what happens? The foot support polygon shrinks to that particular, to the other foot, the foot that is on the ground. So if this is on the ground, it will shift to this, and because now the CG is outside the foot support polygon, it is immediately going to fall in that direction. So the robot will fall in this particular case, it will fall in this direction. Okay. That means we have to balance the system. That is one. The second is when the robot is moving forward. How does it move forward? We have two legs. So this is one leg. So how would it move forward? This is the back leg. It will take the back leg in air and the body will go forward. For example, the body comes to this position and this leg has now moved from here to here. So if you can imagine, the leg is moving and the rear leg has become the front leg now, and the hip has moved forward by this much. So the body moving forward basically means that the hip has moved forward, okay, having some trajectory, and the rear leg also has some trajectory and it has gone forward. Okay, so this is how the robot moves forward. It bends on one side and then takes the body forward, and there are phases of walk which we call the double support phase, called DSP, then single support phase or called the swing phase, SSP, then there is a double support phase and there is a single support phase again. So this means you look at the front view. This is my front view, and please note carefully the front view and the side view. This is my front view and this is the side view. In the side view, one leg is standing, one leg is behind, one leg is in front. So this is the back leg, this is the front leg. Okay, now what it does in the double support phase, which is still here, this is my double support phase till here. The robot bends on one side. Okay, so the robot is bending on this side. So it is, so what do I mean by bending? It is like this, then it comes like this, and it has bent on one side. Now if it bends on one side, what is happening? The CG projection of the center of mass comes onto this foot support polygon now. This is something that we were talking about just some time back, that if the foot support polygon is shrunk, then the robot can balance by shifting the CG this side. And how does it do that? By bending. So what it does is it will simply bend. It is simply going to bend on the other side. So what it does is it bends on this side like this. Okay, so if you can imagine, if it bends like that, what will happen? The CG is now here now. So now the CG is inside the foot support polygon. It is balanced. It is not CG, it is normally zero moment point or center of pressure. We'll come to that. So in the double support phase, it is bending on one side, both legs are on the ground. Okay, in the single support phase, one leg goes up. Please look at the side view. So till here, both legs were in ground. Now one leg goes up, takes a trajectory and goes. So you can see this leg moving. See here, here, here. So it moves forward and then it becomes the front leg. Okay, so this is a trajectory which is going. It is following the trajectory and becomes the front leg now. It is in single support phase. Then both legs are on ground again. And this is again my double support phase. So double support, single support, double support. In double support phase, it bends on the other side now, the other leg. Okay, so if it bends on the other side, what is happening? We're getting this, and then this leg, whichever is the rear leg, it comes front now. Okay, the same procedure is repeated. So if you're standing on front and so this is what it is showing here. Let me go back and try and explain this very carefully. So if I say, let me name these two legs. Okay, so let me call this the left leg and the right leg. So in this particular case, we can say that this is my rear leg and this is my front leg. Okay, so what has happened? The rear leg has become the front leg now. So the rear leg has come forward and become the front leg now. Okay, so the rear has come like this and become the front. So the back leg has become the front leg now. Okay, now this is my rear and this is the front now. So sorry, this is rear and this is front, and this is all double support, so it remains as rear and front. Now what happens? The rear leg is moving forward. The rear leg has moved forward and now it has become the this is the rear and this is the front actually. Okay, so you can see here rear is back, here rear has come in front because the back leg has become the front leg now. Then it bends on the other side. Okay, now the back leg is on the now the front leg is on the ground and is behind now. Okay, so what will happen is it was bending on this side, now it will bend on the other side. If you can imagine, now it will bend on this side. So this fellow is now rear, now this fellow will become front, so it's bending on that side, and this leg will come forward again and become the front leg. So first it bends on left side, then it bends on the right side. So when it bends on the left side, your left foot is on the ground. Okay, and the rear leg is going forward. Now if it bends on the right side, then your right leg is on the ground and the left leg is going forward. So that is what it does. It bends from side to side and to maintain balance in the frontal plane. And in the side plane also it maintains balance by correspondingly looking at the zero moment point. Now what is the zero moment point? Let us discuss that before we go on. So the zero moment point basically is equivalent to this CG. So we talked about CG. CG is for static case. Zero moment point is for the dynamic case. And the zero moment point is also same as the center of pressure. So we don't talk of CG in a dynamic case. So how the zero moment point is computed is that we are looking at a biped robot here, two-legged robot, and this is the leg on the ground. Let's say this is leg on ground. Now this leg is in air. Now if this is in air, then each of the joints we are saying is lumped mass, and these are having masses, say M1, M2, M3, M4. This mass is called as Mi. Okay. Now if you look at this as Mi, then we can say that this one, for example, is M1, just for example. Now when this leg is in air, what is happening is this mass will be attracted by gravity. This mass will be subjected to gravity forces, mg, and acceleration forces, which is equal to I into x double dot. Okay, or we can say mass into x double dot. So these are gravity forces. This is gravity forces and this is inertia forces. So there is one in that direction, one in this direction. Just for example, if the robot is moving in that direction. Now these two forces are at a distance, some distance from the foot on the ground. And hence, what will be the effect of these two forces, the inertia and the gravity forces, is that it will cause a moment in that direction at that ankle point. Okay, because it's in air. Just to simplify it, if the leg is up like this, okay, this is contact, this is my mass, then the mass acts this side, and there is inertia force that side. So mass into acceleration, and mass into inertia force, mass into acceleration, mass into gravity. So this is going to be, if this is my distance x, then it will be x into mg and x into mx double dot. That is the moment acting about the ankle point, right? So if you do that, then the forces that are acting at the contact point is the sum of all forces, which are gravity forces and inertia forces. Okay, so out here there is going to, all these masses are going to have force in this direction, combined of all of them, and there this will be balanced by an equal and opposite reaction. Let's call this FCI. Okay, so there are two forces which are acting. One is due to gravity, and the other is because of acceleration, and the total forces in the upward direction will be balanced by the reaction forces. So this is my reaction. Okay, so there is no unbalance there in terms of the forces only. But if you look at the moments now if you look at the moments which are acting at the ankle, now some moments are because of your gravity. So mg, x into g is, let me call this distance x into g. This is the distance here. So x into g cross mg is the moment because of gravity. This is the moment because of acceleration forces. Okay, now h is the force moment which is acting, if it is acting in the center of the body, h is acting there. Okay, now this has to balance again, right? So what we see is that forces do not cause a disbalance, because the reaction force will always balance as per Newton's third law. But the moments which are acting need to be balanced, because if there is a moment which is not balanced, okay, then it is going to fall in that direction. And how do we get that? So we look at the moment balance equation, and then we see that there are these three moments which are there. So what we do is, I say, if this is my foot, okay, let me draw my foot like this. This is my foot here. Okay, suppose the force here, reaction force Fc, is acting there, and this distance is equal to my Pz. Okay, P into Z is that distance. Then the moment being caused there is Fc into Pz. This is one moment. Now, so this is my Fc into Pz. Now the resultant of the other fellows are there, all the other moments because of this and this and this. The resultant is there. Let me call about this the resultant moment. Now if this moment balances the resultant moment, okay, then only the system is balanced. Okay, which moment? The moment that is caused by the force into the distance, the reaction force into the distance, must balance the other resultant moments which are acting at the ankle. Okay, so if they are balanced, if they are equal, it means that there is no resultant moment at the ankle now. Both of them are balanced. And this distance, this point P, is basically what we call the zero moment point. So for balance, we have to ensure that this point P is inside the foot polygon. If I draw the top view, this is my ankle point. So this point P has to be inside the foot polygon, which is the support polygon. In case of two-legged stance, it doesn't matter, because your foot support polygon is so large. Okay, so it can be anywhere there. For two-legged stance, the system is balanced. But for one-legged stance, it has to be inside this foot. Okay, so if this is my front view and that's my top view, then the zero moment point has to be somewhere there. And how do we calculate it? We calculate it using this equation. Okay, now zero moment point is what we talk in terms of dynamic balance. So we'll be talking in terms of, there are other concepts of balance by foot rotation indicator. Okay, then so basically what we are looking at is the zero moment point. And when it is walking, I forgot to mention very quickly how many degrees of freedom do you need for walking, that I forgot. Now to bend on this side, okay, you can imagine the robot has to bend on this side. Now if it has to bend, it has a degree of freedom here. Okay, so this is 1, and there is 1 degree of freedom there. Now in the side view, there is a degree of freedom here, here, and here. Okay, so there is 1, 2, 3 plus 1, which is here, which is this one. Okay, there is 1 here. So there is 1, 2, 3, and 4 per leg. So 4 per leg into 2 will mean 8 degrees of freedom. So if the robot has to walk straight, only for walking you need 8 degrees of freedom. Okay, for turning you need 10 or 12 degrees of freedom For going an uneven terrain, you may need 14 degrees of freedom. Okay, because this robot cannot turn, it can only go straight. So simply walking straight, you need 8 degrees of freedom. Where are those 8? The first one is in the ankle because it needs to bend the whole body. Then the remaining 3 are at the ankle, the knee and the hip, because it has to bend the knee and then move forward. Okay. Now this is showing us the simulation in the frontal view. The robot is bending from side to side, and the black dot that you can see there, that is the 0 movement point. Okay, the black dot there is the 0 movement point. And the 0 movement point moves from leg to leg. Whichever leg is on the ground, the 0 movement point has to be on that leg. This is in the side view. You can see the 0 movement point moves during the double support phase. So single support, double support, single support, double support, single support, that's the way. Now if I see it in 3D, this is in 3D. This is a figure in 3D. The robot bends on one side, comes this side, then goes that side, then comes this side. And the black dot is the 0 movement point, which has to be ensured. So when we talk of optimization or gait, I have to ensure that these joints, how many degrees of freedom for walking straight? 8 degrees of freedom. So there are 8 variables, theta 1 to theta 8. So I have to do the inverse kinematics such that the 0 movement point ZMP is inside the foot perimeter. Okay, so that is the question that we're talking about. Now, because there are 8 of them, this is a redundant system, which means that you can have infinite combinations. Now, how do you get the best combination in terms of energy? That is something that we'll be seeing today. Now, the 0 movement point, as you can see in this, the black dot there is the 0 movement point. It moves from leg to leg, and it's not static. In the leg also it moves. So it starts at the heel, goes forward, then goes to the other leg. Okay, there's something you can see very clearly. In the human foot also, we use the 0 movement point. So if you look at the shape of our leg, it's very interesting that we also walk exactly following the double support phase, single support phase. So you stand on 2 legs, then lift one leg, take it forward, then bend on the other 2 leg, you come on 2 leg, bend on the other side, take the rear leg forward. So we have 2 leg, 1 leg, 2 leg, 1 leg. Now if you look at, when we take the leg forward, we make a heel strike. Okay, so in the case of the robot, it doesn't do that, but in the case of the human, this is what we do. So this is the other leg. Let me just draw it here and explain. So this is the other leg, which is on the ground. So what we do is this leg goes forward like that. Okay, and the hip also goes forward. So if the leg is like this, it makes a heel strike first, then it becomes flat, if you can imagine. Okay, in the human case, not the case of the robot. So if you're making heel contact, then the 0 movement point is here first. Then as we are moving the body forward, the 0 movement point also moves forward, goes to the big toe, and then goes onto the other foot. So it basically means that these small fingers here, they don't do any work because they don't support the 0 movement point. And hence they're very small because they are not required actually. This big toe is the one that supports the weight, and hence it is required. Again, you have an arc in there. Okay, we have an arc there. Because the 0 movement point does not go there, we don't require any support there. Similarly, the 0 movement point also doesn't go here much. And if you look at your shoes, they wear off in this region. Okay, if you look at the sole of your shoe, you'll find that they wear off. They tend to wear off here. Why does it wear off here? Because when we make heel contact, the 0 movement point is at that point. Okay, and these points don't wear off because the 0 movement point never goes there. So this is very, very important, not only for bipedal walk, but also for shoe design, understanding why our leg is like that. Okay, so now let's proceed and see how does the robot move forward. So in double leg stance, it is pretty clear. Okay, the robot is on double leg stance like this. It has to bend on one side first. So this is double support phase, and this is on, this is my front view. On the side view, if I see, what is happening is, this is essentially to bring the center of pressure onto and it remains there. When it's on single leg stance, it is always like that. Now, what it does is basically, it has to move the body forward. Okay, so the rear leg, so this is my front leg, this is my rear leg. The rear leg has to move forward like this, and in the same time, the hip also moves forward like that. So we have a foot trajectory here, and we have a hip trajectory there. Okay, that's how the robot moves forward. Now in the next step, what will happen? This will become the rear leg, and we'll have another, this fellow will become so in the next step, this has become, the rear has come here. So in the next step, what will happen is, this guy will, this fellow will become the rear, and then it will go forward. I hope you understand that. So our point is that the hip has a particular trajectory. It can be a cubic spline. Okay. Similarly, the leg has a trajectory. Now it can be also a cubic spline. So this means that you can have infinite splines like this. All of these are possible trajectories. Similarly, for the hip, you can have trajectories like this, like this, like this. Okay, they're all possible. So the question comes, what should be an optimal trajectory? Okay. Now, interestingly, if you're wondering what does the human trajectory look like, okay, that's an interesting question. Now, if you look at the top view, in the case of the robot, it's a cubic spline and on a plane. In the case of a human, if I see that this is 1 foot and there is another foot, then this will be sinusoidal. Okay, this is a sinusoid. So similarly, this trajectory is something like this in the case of a human. Okay, it's a sinusoid. Why sinusoid? Okay, this is an interesting question. To maintain continuity. Okay, so for maintaining continuity of motion, this has to be a continuous curve, which is a sine curve. In this particular case, what will happen is you'll get one curve like this, you'll get one like this, like that. So if you're putting cubic splines like this, like this, like this, they're not continuous here. So your motion will be very jerky kind. Whereas if you're having sinusoids like this, then it's a continuous motion. So for the human, it's a sinusoid in 3 dimensions. In the front, it is like this, in the front, and in the top also it is like this. Okay. But for simplicity, we are going to assume that we are going to take cubic splines. We have talked about trajectory planning and we have looked at cubic splines. So we are familiar what it looks like. Okay, so we'll be doing a cubic spline here and we'll do a cubic spline there. Now, how do we proceed? As usual, we have noticed that there are 8 degrees of freedom for the biped robot. So these 8 degrees of freedom mean that there are 8 joints. There are 4 joints. 8 are 4 joints per leg. Okay, so I assign my axis. Z0, Z1 is here. Okay, Z0, Z1. This is my first axis. Now in this particular case, remember, just pay attention that your 0 joint and first joint are different. Okay, this is just for reducing one transformation. There's one axis here, one axis here, one axis here, one axis here. So this is how we are putting our DH parameters. Okay, this is my first axis to bend, second axis, third axis, fourth axis, and 5th, 6th, 7th, and 8th is the same in the front direction. Similarly, if I see from the side, this is my front. If I see from the side, it will look like this. Okay, that's my front and this is my side. Now I have got my transformation from one leg to the other leg. Now suppose this leg is on the ground. I say that the 0 axis or the 0 frame is on the ground. It doesn't move. Then it's something like a serial manipulator. This is the fixed axis. This one link, this is another link, this is another link, this is another link, this is another link. Now you can imagine this to be like a serial arm. Okay, and this is my 0, 0, 0. It doesn't move. It's on the ground. Now the question of inverse kinematics is as simple as that for a serial arm now, because it is one leg is in air, the other fellow is on the ground. Now if you're wondering what to do in the next step, you just switch the zeros here. The next step, what happens is this one is on air and this one is on the ground. So you switch the 0, 0 from here to here now, from the left leg to the right leg, and you can continue. Okay, so the kinematics is very simple because we are treating this like a serial arm with one leg which is on the ground. We say that is not moving. I say that is 0, 0, 0. Now I find the relation between the frames, and what I get is the transformation matrix, which is going to take me from 1 to 4 and 5 to 8. I multiply them together, I get 1 to 8. Okay, so there are 8 transformations because there are 8 joints. There's an 8 degree of freedom system, and I get the relation between the 0th frame and the 8th frame. Okay, and the 0th frame is on the foot on the ground. Okay, now what are the various research issues that you can think about here? I'll just come to the optimization is one of them. How do you get optimal gait? Okay, now one of the research issues is energy optimal trajectory generation for not only for walking, for obstacle avoidance, stair climbing, going on 3D ground. What would be the optimal trajectory or the optimal gait? This is a issue we can look at. Number 2 is, if you put rigid links, there is going to be contact with the ground and the leg, so there is going to be impact. So it will be a good idea to put soft material on the ground or on the foot. Okay. Now you can also look at the effect of soft material on the sole of the biped when it is walking. What plus effect does it have on energy efficiency? We can look at compliance of the joints. We have already discussed the idea of robotics, where we talked about the robot having compliant joints. That means I have a joint and there is a spring at the joint. Okay, what is the advantage is when it is hitting the ground, there is a force which is coming, impact. So this force will be absorbed by the joint. So we looked at a case like this where you have a motor and the motor is rotating and it is not directly connected. There is a torsion spring and this is connected to your link. This is something we talked about or we studied, right? So what is happening is on the link side, which is my leg side, if there is a force which comes, impact when it is hitting the ground, this force will be absorbed by the spring. It will not come directly to the motor. Okay, so effect of compliance at the joints in energy, then compliance in rigid link. I can make the link itself compliant so that when it hits, it bends like that. So we'll look at all of this, what happens to each of this. Motion planning in 3D we'll discuss in the next class when we talk of optimization in planning. That is for the next class. So these are all research issues, and some of this is taken seen or trying when we try to copy human locomotion. In the human body also we have compliance in the joints, we have compliance in the muscles. Okay, now optimization of the leg trajectory. This is how we proceed with the leg trajectory. This is the first research problem, that is optimal trajectory generation for obstacle avoidance. How do we do that? What trajectory are we optimizing? We are looking at optimization of this trajectory. Let me explain it. It's very simple to understand actually. So basically we are treating this like a serial link manipulator. Okay, now in a serial link manipulator, again we have a trajectory here and I have a trajectory here. Okay, both of these are trajectories of the hip and the leg. Now if you look at this, this is like a two link manipulator. It's like there are two links there. In each leg there are two links only. Now if it's a two link manipulator, you know the inverse IK solution for theta 1, theta 2. So a two link manipulator which we talked about like this. Okay, this is my theta 1, this is my theta 2. This is like this is almost like the same two link manipulator is here. So from geometry I can find the solutions. Okay, so if I get this trajectory, I give this trajectory and I give this trajectory. So at every point here I divide this trajectory into 20 points, and for every point here basically we can get a link like this. The link is going forward, you can imagine that, and in each case it's a two link manipulator. It's 2 DOF, two links only. Okay, so I can geometrically find the solution of, if I know this point and I know this point. Okay, so I know those 2 points, so I know this point, I know this point on the trajectory. So if I connect it like this, this is a two link manipulator. Okay, so basically what we are seeing is I can very easily find what is, so every point there has a corresponding connection like this, and it's a two link system, so I can very easily find what are the joint angles simply by doing geometry. So it is not very difficult to do inverse kinematics also. We are doing this geometrically. Okay, so what am I trying to do here? I am trying to find the trajectories, which is the hip trajectory and the leg trajectory, okay, which is going to give me minimum energy consumption. Now to find minimum energy consumption, I have to find the dynamic torque. So we write our dynamic equation using Lagrangian Euler or Newton Euler, where joint torque is equal to inertia into acceleration, Coriolis centrifugal force plus gravity forces. Right, now what is the work done? When the robot is walking like this, this is my hip trajectory and this is my leg trajectory. I can divide this into 20 points. I can find the torques at each of those 20 points. So tau 1, tau 2 like that. And then I can get the work done, tau into d theta dot into dt. Okay, this is the total work done. Okay, on this trajectory only. So what I can do is I can find the work done when the robot has moved his leg from the rear to the front like this and the hip has moved like that. Okay, simply by doing inverse kinematics and then using this dynamic equation. So once we have done that, we can find the total energy for a particular trajectory. So what I can do is I can generate different trajectories like this. You know how to do that. Okay, so if you have a cubic spline, you can change the gradients in the two sides. Okay, or you can put a height and change the height. So similarly, I can put different heights here, and then for each of those trajectories, I can compute what is the work done. And the one that gives me the minimum work, I can say that is an optimal trajectory. So this is how we are doing our optimization of the leg trajectory and the hip trajectory. Okay, so what we have done here is, I'll just explain this very, very simple. So my hip is moving like this and my leg is moving like this. Okay, so I divide that into 20 points. Okay, compute the torques on each of this. I do inverse kinematics like this, and then I compute the torques tau, and then find the work done as shown. I just explained it. Okay, from that I can get my optimal trajectory. Now you can use different optimization procedures. Okay, you can also use a for loop. For example, in this case, you change the two vectors, two gradients on two sides and get different splines. Or you can change the height here, okay, of this spline, and then also you can get the torque. So you can write a for loop which is going to change h. Okay, the height h can be starting off from say 1, 2 like that up to some value. Or you can use something like genetic algorithms. What genetic algorithm basically does is it takes the splines, okay, and what GA does is basically it finds different splines, okay, by finding different combinations of this two sides of these two gradients. This is one way. Now, is there any other way? There is another way of trying to solve this problem. That is, if I don't go to the, so I optimize this now. Now, suppose I don't optimize that, then what? What do I mean by that now? So it means that at the end of the day, I'm controlling the torques at the joints. This is my joint torques. Okay, taus are there. Okay, so basically it means that the robot has moved from here to here. Let's say this is my, and the front leg, it has moved forward like this. So this point has come here, this point has gone there. So this is my front leg now. This has become my front leg. Okay, that is my front leg. It has gone like this. Okay, and the hip has moved like this. Okay, so the real leg has become the front leg and the hip has also moved. Now I need not optimize. This is one way of doing it. The second way of doing it is I did not optimize this joint trajectory. I know the start angle and the end angle of every joint. This θ1 to θ8. So from this figure, I know exactly from inverse kinematics what is θ1 and θ8. At this point also I know what is θ1 and θ8. Okay, so at this point I say θ1 to θ8. This point I say θ1 dash to θ8 dashed. I know the range of each angle. So for θ1, I know what is the range from θ1 dashed to θ1 is my range. So what I do is I optimize each of the joint angles separately. So I don't care about this leg trajectory. It can be any trajectory. I'm going to optimize the range of motion of the joints. I know what is the range of motion of each of the joints, and that is what I'm going to optimize. And we do that again by fitting a polynomial. So I take this θ1 to θ8 and each this, for example, θ1. I know that the total range of walk is or per step is how much time, say for example 3 seconds, just for example. Then it is changing from θ1 to θ1 dashed. This is the initial point, this is the final point. So what I do is I change these 2 points in between and I fit different curves in there now. In the previous case, I was fitting the curve onto the leg trajectory. Here I'm fitting the curves to the joint trajectories. Okay, so I'll have 8 joint trajectories, and I can do the same again. I can use for loops or I can use GA. What GA will do, it will change this point and this point for each of those joints, make different combinations, compute tau, and then I'll minimize the work done. Okay, so minimization of this. Both give the same answer. Okay. Now, if you look at best optimization results, this is something we have done using GA. So the best results we got for an obstacle, for example, there's an obstacle here. It's interesting to see that the trajectory will be looking something like this. Okay, now this is an interesting case because it is showing you an optimal trajectory, showing energy minimization. To climb a stair, the trajectory is like this. This is the leg on the ground. Okay. So what GA is basically doing, it is finding different trajectories at the joint, fitting it and finding for which of this combination of trajectories you get the minimum energy. And then it is saying that is optimal. These are just some GA parameters, population size, crossover. You could use just for loops for varying the trajectories also. But this gives a more exhaustive kind of a result because it covers the full search space. So this basically gave us how to generate an optimal trajectory. Next, we'll look at if you put soft material at the foot of the robot, then what happens? Now this soft material is required because otherwise there's going to be impact when the robot foot hits the ground. Both a rigid body versus rigid body. So there is going to be a heavy impact. Now to avoid that impact, if you put a soft material, then we model the soft material by using a very simple analysis, by using very simple deformation model. We simply use the F is equal to K into del X model. Okay, and we say that the deformation is having a spring constant K, and depending on the force, there is going to be a del X and that is going to change. So very simple model we are using. There is a force here and there is a force here depending on the total force, and we see that it bends like this, okay, on one side. And if you do that, then what we see is that when the force is acting, for example, there's a torque acting and there's a force acting. So this torque will cause this torque is going to cause deformation, something like this. Okay. Now, two things happen. One is that if the material is very soft, please remember that it has to bend on one side like this. When it is bending on one side, there is a deformation which is going on. Okay, so there is a deformation which is going on like this. Now, if the material is too soft, what is going to happen is it will start vibrating. Okay, because the controllers tend to bending it this side, but there is too much deformation and it can fall on this side, so it has to come backwards again. Okay, so what is happening is that there is a lot of vibration going on here. So there is an optimal material, this is probably optimal, where the deformation is right and it does not vibrate about that point. Okay, so we can see that we can put soft material at the foot, but then we have to ensure that it doesn't start vibrating. Okay, and this was the optimal trajectory that we got. We compared the optimal trajectory for a robot with no sole deformation, walk with sole deformation, and we found that it actually takes less energy. It takes 3.16 watts. That means if you add soft material at the sole of your feet, you tend to save some energy. Why? It's pretty interesting, because when we are bending like this, suppose you are bending 10 degrees, just for example, this is my 10 degrees here. So this work is being done by the motor there now, because there's a motor at the ankle. Now when I'm bending by 10 degrees, but suppose I have soft sole now. So because of this soft sole, what is happening is that additional bending I'm getting here, this is passive. Okay, so what is happening is this fellow is automatically giving you some energy, some passive deformation without the motor doing any work. So here it was bending 10 degrees, here it is requiring 8 degrees. Maybe that 2 degrees is coming from the soft material itself. This makes it very clear why the energy requirement is less. Okay, so we see that if you put soft material, it tends to help. So these are some of the robots which are made with soft materials, and we can see it. Okay, this doesn't seem to be working. Okay, next is if you put compliance at the joints. Okay, we looked at soft sole. Now if you look at compliance, now if you look at the human legs, there is compliance at the joints. For example, we have muscles. Muscles are connected by tendons, and these have some kind of stiffness. Okay, so if you make a robot which has compliant joints, then the effect would be that it is like there is springs in the joint, and that is going to affect your energy, that is going to absorb your impact and things like that. Okay, so here what we do is there have been some cases, for example, they have studied carefully in terms of birds which can run very fast. For example, the ostrich. So the ostrich leg muscle is like this. There's the muscle and there is a tendon, and this tendon has stiffness which enables it to run very fast. In the human leg also, we have tendons which are here and here which give us some kind of stiffness. Now, so this is the idea of a biped with compliance of the joints. We had talked about this when we talked of control systems, that you have a motor which is connected to a torsion spring which is connected to the link. So there is a spring in here. So if there is a force in here, it will be absorbed by this one now. Okay, and we write our equation of dynamics, but what you see is that apart from the three terms, inertia, Coriolis, centrifugal, and gravity, one more term comes inside, which is because of my spring. So F is equal to K into del X. So this is my del, or in this particular case, we can say del theta. Okay, so this is my K and this is my del theta term. Now, exactly the same way, what we can do is we can do optimization, look at the various hip trajectory and leg trajectories, and then see which one gives us optimal. Now, interesting to note that in this equation, this is also a variable. Okay, the spring constant is a variable. So basically what it gives is that So basically what it gives, we see that for different values of k is equal to 0 means it's stiff. Okay, and if we start varying k, then we get different energy consumption. So you can see very interestingly that the trajectory is also changing, and for this particular case the trajectory is like this. Okay, and for different time steps also. So here we're looking at the variation of time step. 0.5 seconds is 1 second is 2 seconds for k is equal to 0. That means this is a rigid robot. Okay, now if you are looking at varying k is equal to 0.25, 0.5 and 1 Newton meter per rad, then we can see that the trajectories are actually different, and this is the one that is giving us lower energy. Okay, so if you now plot on the x-axis we have the stiffness of the spring, and on the y-axis we have the work done. What we do see is that for this k we get the maximum, we get the best energy consumption, which means that this we get the minimum energy. Okay, so this does seem to prove that if you put springs at the joints and vary the k, with a suitable k, the k has to be optimal. If you put a higher k, then the energy goes up. So there is an optimal k for which only you get an optimal energy consumption. Okay, so this very clearly proves that if you put compliance in the joints, you tend to save energy. Now we can take this one step further and say that now if I put compliant joints, so for example in this robot, which is a biped robot, if I put a compliant section here, this is my front view, this is my side view. So in this case, suppose I replace this with a compliant link, a C section, then what happens? Okay, so I'm making a soft sole, then I'm making a compliant joint, and now I'm making a compliant link itself. The link itself is compliant. So this is my knee joint and this is my ankle joint. So I replace this joint with a C section, which is made of aluminum. It can have different shapes, and now we can basically do, this becomes more complex because in this particular case, we are looking at the variation of the zero moment point in a sinusoidal curve. Okay, in the previous case, we simply said cubic splines. Now, these are my constraints, which are at the swing ankle trajectory, and the hip is a sinusoid. Okay, and basically what we are doing is we have to find our dynamic equation again, which is this. Now there are two equations. One equation is this one. There is another one because of the stiff of the flexible element. Now one of them is controlled, the other one is not controlled, because this is something we looked at in terms of compliant joint when we talk of control. There was one in which the input was, it was possible to control the input, and there was another one which you could not do anything about. Okay, so we have two equations here. And how do we solve this is basically, during gate we find the torque, assuming that it is rigid. Now if there is a torque acting at the knee joint, then I find what is the deflection because of the knee joint and make the corrections onto this equation now, and then find the dynamic torque again. So you have to do that in a cycle in which you first assume it is rigid, then find the torque, and then find the deflection, and then find the torques again. And we used FEM to model the deflection, which is quite time consuming here, because this is a curved beam, and how much force is acting at the knee joint I get from the dynamic equation, and based on this F I can find what is the deflection, and after it has deflected I have to make this correction again and then find the dynamic torques again. Okay, but once we do that, we can do optimization, and basically we can find what is the trajectory of the biped with compliant joints. So this is a compliant joint biped, and what we are seeing, not compliant biped means compliant link biped. Okay, the link itself, what we see is that if you're looking at the zero moment point, it is vibrating a lot here, and this vibration happens essentially because there is a compliant joint in there, compliant link in there. Okay, and here also when there is transfer of zero moment point, it vibrates. Okay, and that is expected because there is a joint, there is a flexible link there now. Okay, now if you look at the video, this is a case of a robot which is having rigid links. So these links here are rigid. Okay, and you can see that when it is walking, it is bending on one side and then going forward. Okay, that's how the rigid link robot walks. Whereas if you're looking at the fellow with a compliant joint now, so there is a compliant C section made of aluminum here. Now you can see that it will start shaking. The moment it lifts one leg, it is on two leg stance. It has lifted one leg. You can immediately see that it is shaking. Now it is shaking because there is compliance in the joints, in the links, and there is some vibration there. It is good in the sense that for running and jumping it can absorb shock, but it is bad because some kind of instability is brought into the system. Okay, so today we're talking about optimal gait, and we found out how we can optimize the gait of a biped robot. That is, you can fit different trajectories and then find which trajectory requires the minimum energy. We also looked at the effect of soft sole, then we looked at the effect of putting our compliance in the joint, and then a flexible link. So we'll stop here today. Thank you.